As we continue our lecture, we're going to be looking at some more different kinds of energy and a very important principle called conservation of energy, and we'll talk about what that means. Now, previously we've talked about potential energy, and we said that potential energy is the energy that a body has due to its position. For example, we said that the potential energy from gravity was equal to mg, the weight, times the height, h. And the height is what generally changes, and so that's what the potential energy depends on, the position or the height. Now there's another kind of energy. It's the kind of energy that a body has due to its motion, and we call that kinetic energy. So kinetic energy is the energy a body has due to its motion. And there's a formula for the kinetic energy, and we can see the formula for the kinetic energy right here. It's Ke, or kinetic energy, is equal to 1/2 times the mass times the speed squared. That V stands for speed. And so the thing that you want to make sure that you remember is that squared here. If people make a mistake calculating energies with this formula, they forget the square. And remember, that just means V times V. If you square something, you multiply it by itself. And so again, the total formula is 1/2 mv squared, and it's pretty straightforward to calculate. And anything that has mass, which is moving, will have a kinetic energy, an energy due to its motion, given by this formula. The next thing we want to look at is the relationship between potential energy and kinetic energy. How do they relate to one another? And so you can see that we have this sort of winch here that is being cranked to lift this block up over this pulley to some height. And if we lift the block up to some height, and we have given it a potential energy, mgh. How did we give it that potential energy? Well, as we turned this crank, we created a tension in the rope, which pulled the block up with a force. And so the force times the height, that's the work. Remember, force times distance is work. And so we did work to lift this block up and give it mgh worth of potential energy. And remember, we said that potential energy is the energy an object has due to its position. But we said sometimes it can be useful to think of potential energy as stored energy. And so you can see here there's some scissors. If I cut the string, then the block is going to fall down. And that potential energy is converted into kinetic energy, which has a formula of 1/2 mv squared. Now, let's consider this. As the block falls, the h is getting lower. And so the mgh, the weight of the block isn't changing. mg isn't changing, but the height is getting smaller as it falls. And so the potential energy is lowering. But at the same time, as it falls, it speeds up. And so the velocity or the speed is increasing, and so too is the kinetic energy. In a sense, you can think of the potential energy as stored here, and when you cut the rope, that potential energy becomes or gets converted into kinetic energy, the energy of motion. That's what we mean when we say it's stored energy. It's just being held here by this string. It's stored in the system until the string is cut. Now, you might have heard about solar power, which is really a cool thing. But one of the problems with solar power is that the sun isn't shining at night, and so you don't get as much energy from solar power at night as you do during the day. And so one of the things that people have tried to do is to come up ways of storing the energy from solar power so that you can have it available at nighttime. And the usual way to do that is to use batteries. But batteries have all kinds of problems. They can be bad for the environment, and they degrade over time. They're not as good as they used to be. You probably know that sometimes you have to buy a new cell phone because your cell phone battery is kind of crapping out after a couple of years. One of the things that people have started doing is using this kind of system to store the energy from solar power. And so the solar panels, part of the solar panels, use cranks to lift big masses up very high in very high towers. And then at night, they let the blocks of those masses slowly descend, and that releases the energy to turn a turbine to produce more energy. And so that's actually something people are doing now, using this very basic principle to store energy, which is kind of a cool thing if you think about it. Now here we have another example showing how potential energy and kinetic energy relate to one another. And it's the basic simple idea of a pendulum. A pendulum is a mass at the end of a string that's fixed, and under gravity you just pull it back and then let it go, and it swings back and forth, and that's a pendulum. And so if you have a mass hanging from the string and you grab the mass and you pull it up here and you hold it up here, it's not moving, it's got no kinetic energy, it's just got potential energy because you've lifted it up some. When you let it go, it starts to swing down. Basically, it's falling, but the string constrains it to fall in kind of an arcing motion. But as it's falling, the H is getting smaller, so the potential energy is dropping, but it starts moving, so that means you're converting it into kinetic. Here you've got kinetic and potential energy together. At the very bottom of the motion, where the height is 0, there's no MGH at all. It's all kinetic energy. So that's where it will be fastest. And then it's going to swing upward, and it'll rise back to the same height it started. How do I know it's not going to rise higher than that? Because all the energy I have is right here. It gets converted into kinetic, then it gets converted back into potential. There's a rule in nature that you can't get more energy than you started with. And so it's going to swing back just up to its initial height, back and forth. Now, if there were no friction, no air resistance, that would keep happening forever and ever. But of course, in the real world, there is friction. So eventually it slows down a bit. It doesn't get quite as high. And then over time, it just kind of settles back down to its equilibrium position. Let's look at another example. This example says we have a 2 kilogram mass moving at 2 meters per second. And it has its speed increased from 2 meters per second to 4 meters per second. And the question is, what is the change in kinetic energy? In other words, as the object is speeding up, how much is its kinetic energy changing? Now remember, this triangle here is actually the Greek letter delta, and that means change in. So this equation says the change in kinetic energy is going to be the final kinetic energy minus the initial. It's how much you end up with minus how much you started with. That's going to be the change. And so we can just plug numbers into our formula. So the final kinetic energy is going to be 1/2 times the mass times the final speed squared. And you're going to subtract from that 1/2 times the mass times the initial speed squared. And so if I plug in the numbers, the 2 kilogram mass is the same for both terms. We have 2 meters per second. Now, which is that? That's the initial velocity, so that goes over here. The 4 meters per second is the final velocity, that goes there. Don't forget to square them. So if I've got 1/2 times 2, those guys are going to cancel, and the 1/2 times 2 are going to cancel there. Here, I've got 4 meters per second squared, so that's going to give me 16. Here I've got 2, that's going to give me 4 when I square it. And so don't forget to square those terms. 16 minus 4 gives me 12. My units are going to be kilogram meters squared per second squared. That is a Newton meter, which works out to be a joule. So we know the energy unit's a joule, so it's got to work out to be joules. And so 16 minus 4 gives me 12. And so what I find is that the change in kinetic energy is equal to 12 joules. And that's how you can calculate a change in kinetic energy. The next thing that we want to look at is something called the work energy theorem. And basically it tells us how kinetic energy is related to work. And what it says is that the work done is equal to the change in kinetic energy. Now remember that work is equal to a force times the distance. And if we're being really careful, we would say it's the parallel part of the force times the distance. But work is equal to force times distance. And that work has to equal to the change in kinetic energy, which is 1/2 mv final squared minus 1/2 mv initial squared, as we've seen previously. And so if I do work on a system, what does that mean? So I've got a block here, and it's got some mass, and I apply a force to it. And that force is applied over some distance. We can call it the change in x as the distance the block moves. Well, what's going to happen is I apply a force. It's going to accelerate. Its velocity is going to change. If you apply a force, F equals ma. You get acceleration, right? That's what we said. You apply a net force, you get an acceleration. An acceleration is a change in velocity. So as I apply a force over this distance, this guy's going to speed up. And what the relationship is it's going to speed up according to the change in kinetic energy. And the work done is equal to the change in kinetic energy, so that'll tell you how the initial velocity and the final velocity relate to one another. Let's look at an example using this principle, the work energy theorem. And so we have a 4-kilogram block slides across the table. Its initial velocity is 6 meters per second, and it comes to rest after sliding 10 meters. So remember, comes to rest, that means it stops, right? So it comes to rest means that it stops. Now, what can we do to work this problem? We can note that the part A asks, what is the work done by the force of friction? And part B asks, what is the force exerted by friction? Well, the problem doesn't say anything at all about friction, so how are we going to work this? Well, we're going to have to put our thinking caps on, and we have to recognize we don't know what the work done by friction is, but whatever it is, it must be equal to the change in kinetic energy, because friction is what's causing the block to slow down as it's sliding. So, I have this block which is moving with some velocity, and there's a force of friction which is causing it to slow down. And so we know the initial velocity is 6 meters per second, and the final velocity is 0 meters per second. Its mass is 4, so we can say that the work done by friction is equal to the change in kinetic energy. That's 1/2 mv final squared minus 1/2 mv initial squared. And we can just plug in the values. Now, the 1/2 m in each of that case is going to be 1/2 times 4, which is 2. So I'm going to have 2 kilograms times the final velocity, which is 0 meters per second squared. Doesn't really matter because it's 0 is 0. But then that's going to be minus to 2 kilograms. Remember, that's 1/2 4 gives me 2 times 6 meters per second squared. And what does that give me? That gives me 6 squared is 36 times 2 is 72. And it's minus here, so I get that the work done by friction is equal to minus 72 joules. Now remember, we talked about this idea that if you have a negative work, that corresponds to an object slowing down. And so when we calculated the work for an object we know is slowing down, we got a negative answer, so that makes us feel a little bit better that things make sense. Now part B asks, what is the amount of force exerted by friction? Well, we know that the work, which we just calculated, is 72 joules, or minus 72 joules. That's got to be equal to the force times the distance, and we're given that the distance is 10, so that's equal to the force times 10 meters. And when we divide negative 72 by 10, we can solve for the force, and we get negative 7.2 newtons. Because a joule is a newton times a meter, you divide by meters, you're left with newtons. And again, we have a negative force. What does that tell us? That tells us the force is to the left. And that's exactly what we would expect. Now, in this example, we're going to expand on what we talked about with the pendulum example. If you remember just a few minutes ago, we were talking about a pendulum and how if you let it go, it loses potential energy but gains kinetic energy on the way down. And then the reverse is true on the way up. It loses kinetic energy as it slows down, but it gains potential energy as it rises. What I didn't say, but what is absolutely true, is that at every point in the motion, if you add up the kinetic plus the potential energy, you get the same amount. It's a constant value. The sum of both kinds of energy is always a constant. And so here we can say, I'll just write this out. So I've written down the qualifier here. If no external forces act on a system, that is, this guy over here doesn't have a jetpack providing thrust or something. He's just leaping off this tower and falling. And so there's no external forces acting on the system. We're only considering gravity in this example. The total energy is conserved. And that is the relationship of conservation of energy. So let's look over here at this guy. He's standing on this tall platform. He has mgh worth of potential energy. And if you calculate it, you get 10,000 joules of potential energy. Now he's just standing there, so he's got 0 joules of kinetic energy. His velocity is 0. His speed is 0. He's got no kinetic energy. 1/2 mv squared, v is 0. Kinetic energy is 0. But he's got mgh worth of potential energy, 10,000 joules. So what's the total energy? The total energy he has in the system is 10,000 joules plus 0 joules. That leaves you with 10,000 joules. As he steps off the platform and dives downward, the h is getting smaller, and so his potential energy is decreasing. Now, at this point in the motion, his potential energy has decreased to 7,500 joules, but what does the total energy have to be? It's got to be 10,000. So you know that at that point, the kinetic energy has to be 2,500 joules, because 7,500 plus 2,500 is equal to 10,000. Now, as he continues to fall, the h continues to get smaller, and at this point, halfway through the motion, he's gone from 10,000 joules to 5,000 joules. And how much energy has changed? He's lost 5,000 joules of potential energy. It's been converted into 5,000 joules of kinetic energy. But again, the sum, the total energy, potential energy plus kinetic energy, is still 10,000 joules. He continues to fall, and as he gets lower, at the point when his potential energy is 2,500 joules, what's his kinetic energy? Obviously 7,500 joules. Why is it obvious? Because the 2,500 and the 7,500 add up to 10,000, as they must at every point in the motion. Even the points not listed in the problem. The point here, what's the energy got to add up to? 10,000. Right here, what's the energy got to add up to? 10,000 joules. That's right. And then at the very bottom, the h is 0, so the potential energy is 0. It's got no height, but the kinetic energy is 10,000 joules. It's 10,000 joules all the way through. Now, if no external forces act on the system, I made a joke about him having a jetpack, but there is one external force that we're ignoring here. Air resistance, friction. We know that's a thing. And so as he goes through the air, as the wind or as the air resistance sweeps past him, it's going to create friction heating, and he'll actually be a little bit warmer at the bottom. So he won't have exactly 10,000 joules. He'll have 10,000 joules minus however much is lost to friction. But in a lot of situations, those losses, we can pretend they don't exist because they're so small. And so we can say in a lot of situations that basically there are no external forces acting on the system, and so the total energy is conserved. And by the way, in that situation with the friction, if you add up every possible form of energy, it's still conserved. And so if he ended up with 9,000 joules of energy here instead of 10,000, guess what? That would mean 1,000 joules of energy got converted into heat. We'll talk about heat later in the semester, but that's the basic idea. If you can add up all the pieces of energy in a system, they're always going to add up to the same amount because energy is conserved. Now here's one last example, and I am going to work it for you, but I want you to try to work it first. Pause the video, sit down and see if you can figure it out. I know that there's a temptation to just keep the video playing and not do the exercise, but I promise if you do that, you're not going to get as much out of this video. If you actually do these exercises when I tell you to, it will really help you understand this stuff. Because even if you get lost or you get it wrong, if you just try, and then you see the answer and you see what your mistake was, that's when light bulbs go off. And so that's really, really helpful. Anyway, pause the video, and I'll be back in 3, 2, 1. Okay, I hope you really pause the video. Here's our example. It's a 3 kilogram mass. It's dropped from rest. That means the initial velocity is 0 at a height of 10 meters. We're going to use conservation of energy to find out how fast it's going when it hits the ground. All right, I've drawn my mass here. It's going to fall some height, h, and I've got its initial position and its final position here. What's the energy at the initial position? The energy at the initial position is 1/2 times the mass times the initial speed squared plus mg times the initial height. That is the potential energy it has at the first position, the initial position. And that has to equal 1/2 mv final squared plus mgh final. And so this is the kinetic energy it has in the final position and the potential energy it has at the final position. Now, that may look a little complicated, but it simplifies really nicely because we can say that the initial speed, v initial, is 0. How do we know that? Because it's dropped from rest. It has an initial velocity of 0. And so anything multiplied by 0 is 0, and that whole term goes away. There's something else that's equal to 0 in this problem, the final height. Because the final height is on the ground, and so the height is 0 there. And so that whole term goes away, and what we end up with is mg times the initial height is equal to 1/2 mv final squared. Now here's another fun thing. Mathematically we can say there's an m on that side and an m on that side. Every term has an m. You can divide by m and cancel all those m's. And we're looking for VF, so we can solve for that. So if I multiply both sides by 2, that 1/2 will cancel, and I'll end up with a 2 there. And I get that V final squared is equal to 2 times little g times the initial height. And that's going to be equal to 2 times 10 meters per second squared. That's our little g. Really, we could plug in 9.8 if we wanted to be really careful, but 10 is good enough for what we're doing here. And then h is the 10 meters, and that's equal to the final velocity squared. If I want the final velocity, I just need to take a square root of every term. 2 times 10 times 10 is 200, and so we get that v final is the square root of 200, and that is equal to about 14.1, and the units of velocity or speed are, of course, meters per second, and so our final speed is 14.1 meters per second.